More to do with the inverter build. Here is the breadboarded version of my circuit. We have here three 4000 series CMOS. These, I don't know, 20 cents each. We have two 4011 dual flip-flop data flip-flops, one 4093 quad SMIT 2-input NAND gates, and down in there we have a LM311. God, they've got to be worth 10 cents each, I suppose. Probably I buy things like this in quantity, so one off maybe $1. We've got about, I don't know, 20 resistors, a few capacitors. To be fair, I haven't got everything on this board. I haven't got a voltage regulator. I'm running that off my power supply, so I don't need this to be built on the board. And I haven't got the fan controller, but I've got the temperature controller, and I've got everything on here. I've also got it hooked up to the oscilloscope, which I'll explain these traces to you in a moment. It's a 4-trace scope, so I've got 3. The screen's getting a bit busy to have 4 outputs on there, but I'll get to that in a minute. And here, hopefully you can see this, I've set the camera up to be really fine resolution, so this is the circuit diagram, and as you can see there really is bugger all in it. In fact, I'm still amazed just how simple it turned out to be. Mind you, in saying that, simple circuits have a habit of being more complex in operation, because I remember back in the colour TV repair days that manufacturers chose every little fudge and trick in the book to try and do more with less. Price was the big issue with colour televisions. But however, this circuit does everything that we wanted it to do. Okay, now, by way of an explanation, we have here this potentiometer here is substituting for magnetic screwdriver. Look at that, substituting for our V-sense rail, because we haven't got any output stage on this. This is just the control board, and we have to feed certain external signals in to actually get it to work. So I can alter the V-sense rail, which effectively tells me how much load is on the inverter in the completed version. So when I say I'm twiddling the pot, that's the pot I'm twiddling there. Now just another mention here, I've got the bottom trace is the output of the driver to the FET. So that bottom trace is the signal. That's that one there. Oh no, that's that one there is the signal to the gates of the FET. So the higher that signal is, the FET's on. Low, it's not on. The middle trace is the 800 Hz signal from the capacitor on the input of our oscillator gate. There's that rail there. I'm monitoring pin 2 of the LM311 on the middle trace, and the top trace, I haven't explained this properly, this here is derived from there. The 100 Hz signal, there's my pointer, the 100 Hz signal goes down through a 12k resistor to a 1 microfarad capacitor to ground. This is a first order low pass filter is what it is. So we have a square waves coming in here, we're going to have a triangle wave here, and that is fed down to pin 3 of the same comparator, the LM311. So that is the top trace. So the bottom, they're both sawtooth or triangle waveforms, it's just that one is 8 times faster than the other. And this is how we get our sine wave rendition. done with pulse width modulation. So if we watch the traces, now I'm twiddling the V-sense. So we're going to put the inverter probably in the middle of its range. This is where the inverter will be running, dependent on its power output, but it's pretty much running there. That would be its normal running point. And if we reduce the load, we can actually see the pulse width is decreasing. That's the bottom trace, to the FETs are effectively now completely off. Now as we increase the load, you can see the FETs coming on. I'm twiddling the pot again, increasing or decreasing the voltage, and you can see that the FET now is getting a full sine wave rendition via the PWM, and when it gets almost to the overload point, which is right there, it's now outputting in a square wave. It just cannot cope with the load that we've put on this thing. It's just at the point of overloading. Now if we go a little bit further with the load, we get to the point where now it's gone into overload and shut itself down. And this is exactly what we want it to happen. Now if we leave it in an overload state and we cycle the power, watch the bottom trace. I'll turn the power off. Now you see that? There's our power on reset. The bottom trace actually comes on for about half a second or less and gives just enough pulses to get the V-sense rail back up into its common mode range of that LM311. So I've just adjusted the pot. I'll adjust the pot to tell the control board now that we have actually got voltage on the inverter, on the V-sense rail, sorry. So now we turn that off, we'll recycle it, and it comes up running. It's not the best demonstration, but you know, that's all I can give you at the moment. Now if we drop that one there, no, we've got to do that one. If we raise that one over to there, now these are two inputs to the comparator. This is how modulation works, pulse width modulation works. You can see our DC level, we're changing it, and it's rising up and down, and you can see that the pulse width varying at the bottom to the point where now we've lost it entirely. Oh god, I'm talking too much. So that's PWM 101. Now if we wind that back down so it makes sense again, and get rid of that. I don't know why this is drifting. Yes I do. Get that up there. Now if we watch the bottom rail, I'll turn my soldering iron on. Now remember, this is the signal going to the gate of the output FETs. We've got two phases here. This is just one of them. The other one is identical to this, except it's 180 degrees out of phase exactly. It's a complementary output because we're driving the two FETs and basically in push-pull. So now I'll get my soldering iron, and that there, I've got the diode. This is the temperature sensing diode right there. If I hold the iron onto that, we can heat that diode up. This diode is actually going to be mounted on the heatsink, so it monitors the heatsink temperature. Now as you can see, if I heat that up, just watch the bottom trace, and as the diode heats up, our inverter's just shut off. Take the soldering iron off the diode and it cools, the inverter turns back on again. So our over temperature sensor also works exactly as predicted, and what a good thing that it's going to be. As I say, I haven't got the fan controller hooked up to this yet, but I know that'll work, so we really don't have to breadboard that. The basic idea of just breadboarding all this was just to make sure they had all the logic correct, because if you get signals upside down you'll end up with a reverse sine wave. So it peaks at the zero crossing, it suddenly becomes high and then dips in the middle, and we don't want that sort of caper going on. So there is the breadboarded version and a few scope traces of proof of concept of this design. So the next thing is to get it back onto a circuit board. So I'll tidy it up a bit, just finalise a few of these component values, but it's pretty non-critical, as most of it's working in the digital domain. It's you know, not really critical. The only critical thing's probably around the LM311 area, because that's the heart of the whole thing. It does everything. So yeah, it's probably worth spending maybe $1.20 on a LM311 because of all the work it does. But there's the regulator circuit. I haven't got that on the board because obviously I'm running it on a regulator power supply, so we don't really need to build that. But the rest of the circuit, I think you've seen enough now to be able to probably scribble that out for yourself if you're interested, and try and follow it through. It's, yeah. Okay, I'll load that up and see what we get.